Now let's talk about the variance of discrete random variables. The definition of the variance is that it is the expectation of the square difference between that random variable and its expectation. So this is the expression right here. So you see here I'm taking x, I'm subtracting from x its expectation, I'm squaring it all up, and I'm taking the expectation over that. So if you wanted to write this in more detail, you would actually write the sum over x of little x minus the expectation of capital X, which is just a number, of course, here, squared times p of x. So you can think of the variance as the spread of the random variable about its expectation. So the bigger the variance, the more you should expect the random variable to vary around its expectation. However, you should not take this too literally for discrete random variables, because as we said before, the expectation of a random variable itself may not be a value that the random variable actually takes. Alright, so let's now prove some properties of the variance. Here's a very common property. The variance of x plus a constant is just the variance of x. So how do we prove that? We really don't have to use anything more but the definition of the variance. So this is the variance of x plus c. By definition, this is the expectation of x plus c minus the expectation of x plus c squared, and we take the expectation of this entire thing, and then inside the square we can use the fact that this term right here is nothing more but the expectation of x plus that constant c, and you'll see that this constant and that constant, they're going to be eliminated, and then what remains is the expectation of x minus the expectation of x squared. Here's another useful property. Take any constant lambda, then the variance of lambda times x is lambda squared times the variance of x. Let's prove this as well. We have the variance of lambda times x is equal to the expectation of lambda times x minus the expectation of lambda times x squared, and the term inside the square, this term right here, can be written as lambda times the expectation of x. So I can rewrite the entire expression as the expectation of lambda times x minus lambda times the expectation of x squared. So I can now take out of the square lambda, and I'm gonna have to square it in order to do that, and this is what I get. And now I can use the property of the expectation, that the expectation of a constant times a random variable is that constant times the expectation of the random variable. So here I'm gonna get lambda square times the expectation of x minus the expectation of x squared, which is nothing more than lambda squared, the variance of x. This is an extremely important identity that connects the variance to the expectation. It basically states that the variance of x is equal to the expectation of x squared minus the square root of the expectation of x. And it is a formula that you should remember because it's one of the few formulas that you can use to analytically calculate the variance. Also later we're going to use it to create a sampling average approximation of the variance. Alright, so how do we prove this? Again, we should not panic about it, we should just write down what is the definition of the variance. So the definition of the variance is the expectation of x minus the expectation of x squared. Now what we're going to do is we're going to expand the square, so let's do that. we have x squared minus 2x expectation of x plus expectation of x, the entire thing squared, and we take the expectation of this entire expression, and then we're just going to be using properties of the expectation. So first we can use the property that states that a random variable, the expectation of a random variable plus a constant, so that would be the random variable, this would be the constant, is simply the expectation of x squared minus 2x expectation of x plus expectation of x squared. And then we can further simplify the leftmost term as expectation of x squared minus 2 times the expectation of x squared plus the expectation of x squared, and that of course is the formula that we have up here, and that constitutes the proof.